questions? Any questions before we get started? Oh, let me remind you all, I'm 99% sure I sent you all an email, but actually I've got kind of a lunch meeting. I'm going to be out of the office from 11 till 1 today, but other than that, it's business as usual. Let me know if that's a problem. So I want to go over, I'm going to go over this example that I did last time a little bit and do a little bit of computation. Then I'm building up one of my favorite theorems ever. Really cool theorem. But let me go back to this example. Let's look at now I asked you to take a little bit of this on faith. You're still going to have to take some things on faith, but I'm gonna go through some details anyway about this. And like I said, I'm hopeful that in the fall I'm going to teach a course like a topics course to cover this kind of thing a little bit more in depth. It turns out it's C4. And last time it turns out that all I gave you last time was class number. Let me put an idea on every class. Generating class. So what I'm doing is actually, of course, the group over here is multiplicative, right? And you're not adding these things, but this is the homomorphism, the isomorphism to the additive group C4. And so, of course, what this means is this class right here has order 4, right? This class has order 2, and these two are inverses of each other, right? So I'm going to justify some stuff here that I said last time. What I sort of gave you sort of cold open was that this had class number 4 and that these were representatives of the classes. Also recall if the radical negative 14 is in the ring, then the norm of a plus b radical negative 14 is a squared 14b squared. So using the norm will be helpful at a couple of junctures. Okay. The first thing I'm going to do is I'm going to follow up on the guidance that Jared gave us last time about, okay, we can really be sure of ourselves, given that the class number is 4, we can really be sure of ourselves that, for example, we square this and find that it's not principal, right? So let's see what it looks like. If you look at 3, this is in this ideal class 1 bar. When you square it, this is 9. And what is this thing squared to, which is something creepy like minus 13 plus 2 radical negative 14. Now, I'm here to hope that this thing is not principal. Notice that the norm from 9 is in 1, right? And the norm of 3 plus 3 radical negative 14 is 9 plus 14 times 9. So that's going to be 135. Agreed? And the norm of minus 13 2 radical negative 14, that's something like 169 plus 56, which is 2.5. So I've listed this, the square root of this ideal can be generated by those three things. In fact, we know that, I mean, if you believe what I told you last time, in fact, that ideal should be able to be generated by two things, right? But it doesn't matter. I can use the three generators. How does this go?
If it were principal, we could narrow down the one with the.
Okay, right, so let me kind of look at this. This is 3 to the 4th power, right? And this is 3 cubed times 5, isn't it? And conveniently, this is 3 squared times 5 squared. So let's see if we can play Sherlock Holmes on this one. Just so I don't have to write it every time, let's call that p squared. So the original is p. So p squared is determined by alpha. Then what are my choices? I've probably got choices. Well, the first thing that I notice is that the norm of alpha has to be a power of 3. No escaping that, right? Because if alpha divides 9, then the norm of alpha divides the norm of 9, and the only, which is 81, and the only thing that divides power of 3 is power of 3. It's an integer. So for sure, I know that this is 3 to the k, where k certainly less than or equal to 4. But I can improve that. In fact, k is less than or equal to what? 2. Because this power of 3 also divides this, which rules out 4, and also has to divide this, which rules out 3. So in fact, I can improve this to k is less than or equal to 2. So if p squared is principal, then the norm of alpha must be 3 or 9. Now, of course, here's the faith that's required here. You might say, well, what about 1? Right? Well, this is a proper idea. This isn't the whole thing. And if you believe that this is non-principal, you have to believe that in the first place. But since it's a non-principal ideal, you don't have to worry about the generator being a unit. Everybody okay so far? So now I find myself in doing number theory and ask myself, what are the solutions to a squared plus 14 b squared equal 3? Ain't no solutions to this. Right? You cannot express 3 as a square root of 14 squared. How about solutions to this? Now for that, there are solutions. However, the only solutions, b can't be anything other than 0, because then it's too big. It's very convenient that that's a plus and not a minus. But if b is not 0, it's too big. And once b is 0, you see that you only have solutions. Must be plus and minus. That's it. Right? So P squared equals 3, is that possible? How come?
You look at the form of P squared, one of your elements is divisible by 3.
That is correct. Notice that, actually, what I put away to do this. Right, notice that. Generator. Right. So for this to be the ideal generator by 3, that would mean that 3 would have to divide this thing, which it clearly is not. So that brings justification. So P squared is not principal. So, for example, among other things. So, in particular, C squared root negative 14 is not a UFD because it's got a non-principal ideal, right? And remember, if you have a Dedekind domain, it's a UFD if and only if class number is, or class group is trivial, right? Here is sort of a concrete way to see this, and again, we can use this ideal a little bit. If you move the element 81, right? And I also claimed last time that this was 5. Lucky guess, or how did I come up with this, right? Well, let me, and in fact, let me point out, that not only does this not have unique factorization, but I'm gonna try to justify that these things are all irreducible. And, so if you believe me now, that these are all irreducible, notice I can factor this one way into 2 irreducibles and another way into 4 irreducibles, right? So let me kind of justify that a little bit. Um, by the way, my notation comes from, these are ideals in. How many of you have seen down law theory? Most of you gone down that path. Well, let me point out that there are 2 automorphisms of this ring that are basically obtained by restricting the automorphism of the field extension. Basically, the 2 roots of the polynomial x squared plus 14 are conjugated, right? One automorphism is the identity, and the other one takes a plus b radical negative 14 to a minus b radical negative 14, and that's actually where you get the norm. You take the element times its conjugate, and you get the norm here. And that's why this notation here is suggested, I think, because P bar is the image of this prime ideal under this automorphism, right? I haven't justified that this is a prime ideal, but it is. You actually, what you might do is, if you want to justify that this is, once you know that this is maximal, this one has to be maximal because it's the automorphic image of the other one, right? Mod out by this ideal and see what you get. You should actually get fields when you take z radical -14 and mod out by 3. And a tricky way to do that is look at z mod 3 and see what happens when you join square root -14. By the way, yeah, let's kind of do that competition. But what happens when you have z? What happens when you mod out by this? I'm going to play this kind of fast and loose, so this is kind of computation. You can justify this fairly easily, though. Notice that 3 is in this ideal when you quotient out, right? So that means that every multiple of 3, they're all equivalent, right? So if you take a plus b radical -14, right? Actually, you're mod 3 and then mod some more, right? If you look at a plus b radical -14, then what this means is 4 and 1 are the same thing, right? For example. So think of this as z mod 3 joined with right, and you also want minus 14 to be 1. Okay. Right, so right, so z mod 3 to join with -14. So to speak, that's pretty sloppy. But now, what happens when you get z mod 3 radical -14? Right. So in other words, can somebody kind of describe what happens when you have z mod 3 and you join radical -14?
You've got 9. 0, 3, 2.
Right. So let's see. So what you're doing really is you're taking Z3 and you're joining -14 to it. So what is -14 mod 3? Okay. So right, doesn't it? So how can we interpret this here? So notice that is, yeah, that's right. So notice also that also note agree with that? So, yeah, I feel like, oh, yeah, so. This is square root of 1, so that's -1, so modding out by 1. Yeah, so I'm really not doing this very well. So let me kind of go back here. So let's think of this as, think of this as modding out one piece at a time here. So z square root -14 mod 3. So this is mod the ideal generated by 3 and z radical 14. And so this is the set of a plus b, and I'll put my bars over radical length of 14 with a, b, and z. Okay, this is kind of a better way to think about it. So let's mod out just by 3 first, and you get this. Everybody okay? The cool thing about this, and you do the computations just like you would before, you can just take 14 mod 3, right? So this is just a symbol for now, but when you square, for example, radical negative, when you square radical negative 14, you get negative 14, which is the same thing as 1. Right? What kind of structure does this have? Well, notice that, notice this isn't a field, right? Because, of course, this piece by itself is, if you just take constants, this contains Z3, it contains a field, but it's an extension by a zero divisor, because again, if you look at 1 bar plus 1 bar radical negative 14, comes 1 bar minus 1 bar radical negative 14. You get 1 bar minus 1 bar radical minus 14.
Also,
I'm sorry?
also we know 3 is maximal because P is proper. So we know it's not a field that way.
Right. So yeah, so this ideal is actually bigger. So that's another way you can do it. But yeah, absolutely. So this is going to be 1 bar and then another 14 1 bars. So this is 0 bar. So this actually has non-trivial zero divisors, right? So how do I move on up? Well, let's see. Right, so notice that, note that I'm on that 1 plus. Notice I essentially I just proved this, right? Zero divisor, right? And max. Right? Because what you're doing is all right, 3 is you're taking a further quotient by declaring that one is equal to minus 14. And so when you mod out by this full bit right here, what you're doing is you're taking this bit and you're declaring 1 is equal to minus the square root of negative 14, right? And what happens when you do that? Well, when you do that, you're left basically with 3 cosets. So this is isomorphic. See, 3. Right, okay. And so in particular, this is maximal ideal because when you quotient out, you get the field Z3. This is the automorphic image of it, and so it's maximal ideal as well. So let's try to come up with that factorization. We did this last time. If you look at P bar, if you look at the generators of that, you get 9, 3 plus 3, radical negative 14, 3 minus 3, radical negative 14, and 15. And so this is the ideal generator by 3. Because 3 divides everything in here, and of course the existence of 9 and 15 in the ideal 3 is in. So this is the ideal generator by 3. So when I look at the elemental factorization, and I'm going to think of this principal ideals, this is P bar, P bar, P bar, P bar. Right, okay. By the way, I'm going to go a little fast and loose here again, but in this ring, what was the norm of 3? 9. Okay. So P and P bar is symmetric. So if you could assign a value to the norm of an ideal, and you can, and in the future I'll talk about that too, what norm do you think you would assign to it? If you wanted the norm, if this has norm 9, and this thing equals this thing, what norm would you want to assign to the prime ideal P? 3. Everybody agree with that? Norm of prime ideal P, norm of P bar is a norm of 3, which is 9. And that's exactly the way it's going to work out. I also said that the class group was Z4, right? That means the 4th power of anything is a principal ideal. So those two must be principal ideals. Now P, we actually proved earlier today, P squared was not principal, right? And it's an element in a class group that has order 4. If you square it, it's not principal. It has to have order 4, right? That means that P to the 4 is a principal ideal, but no smaller power of P is principal. Agree? P is not principal, P squared is not principal, P cubed isn't principal, P4 is principal. So that means that this must be generated by irreducible, and same with this conjugate. So now what we need to do is, we're on a hunt now. Right? We're on a hunt for the generator of P4 because I'm thinking that's a principal ideal. And the norm what do you suppose the norm should be? if the norm, if we kind of convinced ourselves maybe the norm of P should be 3, my goodness, I hope the norm of this is 3 to 4, which is 81. Agree? So let's go back to the norm and see if we can find an element of norm 81. And I've sort of sloppily sort of argued that this is irreducible, and I'll be careful about it when I look. So alpha is A plus B radical negative 14. We're on the hunt for this thing that has a norm of 81. And we want this to be equal to, we do this. And again, I am the luckiest dude to come down the pipe because this is a positive sum of, this is sum of 2 positive things. And so I've only got finitely many things to check, right? These problems are much harder if it was a squared minus 14b squared. That's a taller order. But here it's doable. Is 81 itself a square? Yeah, but that seems boring, right? So I want something a little bit more exotic, right? Because I want something that just straight, because the solution that I have for norm alpha equals 81 in the silly case is 9, right? Because the norm of 9 is 81, but 9 is not irreducible, and I was hunting for an irreducible anyway. So go through it. Start jacking up to B, right? B equals 0, we've got a solution. B equals 1, 81, subtract 14 is 67, that's nobody's square, right? But if you try B equals 2, you get 56. 81 minus 56 is 25. So there is a solution. So let me point out that we get the following factorizations. That's 81, which is 3 to the 4th. Now let me quickly convince you that these are all irreducible. Norm of 3 is 9. So only proper divisor. So proper divisor must have norm 3. And that ain't gonna happen, right? Because you can't write 3 as a square if it's 14 times a square. Okay, how about the bigger one? So well, actually, let me go through the whole thing. Right, I'll be complete about this. There's a little bit of overkill on this. Okay, can't be 1 because then it's unit, and it's not proper. Can't be 81 because then other factors, you know. Right? So far. We've already seen that 3 can't be written as a square plus 14 times a square. And I don't even need to check 27 to know this is a not. Why? That's right. So if I could factor this down into alpha beta, if alpha has norm 27, beta has to have norm 3, and that's impossible. Right. Okay, well, norm 9 is a possibility, but the only possibility is alpha is plus or minus 3. That's it. That's the only thing going 9, which does not divide 5 plus 2 radical negative 4. It clearly does not divide it because there's no 5/3 plus 2/3 radical negative 4 in there. So the upshot is, this is irreducible. And so its automorphic image has to be irreducible as well, and the proof is the same. Okay, so there you have a pretty exotic factorization. Notice, I will throw this in, actually. The class group also tells you something else. If you look at the example we did last time, when z is equal to square root of -5, I kind of remarked in passing that it doesn't have unique factorization, but every time you can take an element factored into some irreducibles, you will always get that they have the same length. This is not the case here. Right, this has length 2 and this has length 4. You might ask yourself, are the lengths more extreme, right? Because now you've got the ratio of the length of this factorization, this one's 2, right? This is twice as big, right? And then the answer is for this particular ring, that's the biggest ratio obtainable, right? There's something called elasticity that basically measures the ratio of the longest factorization to the shortest. Actually, in general, you have to do a supreme kind of thing. But the longest factorization to the shortest is called elasticity. And again, for rings of algebraic integers, the class group tells you how big the elasticity should be, which is kind of cool. Okay, any questions? Okay, so let me give you another example. I'm not going to work through all this. I'll probably just work in one direction of it. So I've skipped over a couple things in the notes, repetition of characterizations of UFDs. And so if you have so let's suppose let D how did you heard the square free integer? That means that no square except 1, except the number 1. So for example, -1 is a square free integer, -2, 7 is square free, 105 is square free, but 12 is not, because it's divisible by an underscore square. It turns out, and you may have seen this, maybe not before, but it turns out that every quadratic extension of rational numbers is of the form Q adjoined with the square root of D, where D is the square root. Why is that? Well, let me give a quick justification for that. Here, A, B are integers. And I will assume that neither one of them is 0, right? This is the same thing as Q. Because of course, square root of B squared is B, and I can absorb that into the Q part, so this is this, right? So in particular, so any quadratic extension. Well, let me start off by saying quadratic extension is a form. So any quadratic extension is a form Q adjoined with n, where n is the integers, not zero. Correct? So we've reduced it to that. And so now just take n. That way. So now my extension looks like this. And in fact, let me write this more conveniently. P1, 1 plus 2 and 1. P2, 1 plus 2 and 2. PA, 1 plus 2. Right, the powers are greater than or equal to 0, otherwise I wouldn't write the freaking prime in the first place. And these ni's can be are greater than or equal to 0, right? Now, if I take the square root of this thing, like that, notice if I can pull all the squares out. And times P1, M1, but again, this bit right here is just an integer. So I'm going to write the numbers, let's absorb them there. And so here we go. There's your square free integer, and it can be positive or negative. One more thing is, by the way, there's one more thing you should criticize me about, not just the way I dress, but about that. Can anybody think what that is? Well,
necessarily have to be the square root of a rational number.
all right. So it would be a mistake to say that every cubic extension looks like this. Because not every root of the cubic equation is a perfect cube, right? Because, for example, if you look at that, the root of this that you adjoin is not a perfect cube. So it's problematic. How do I know that all I have to do is adjoin the square root of something? Well, an arbitrary polynomial on the quadratic looks like that, right? Or it's monic. I can divide out if I like. And this is, if I use the quadratic formula, and I have to take more time to erase this because it's embarrassing to do this 9 times one class, but that's what we get. So really, this quadratic extension that you get by joining the root of this, you would join this. Now, there's a couple of things that are neat about quadratic extensions over the rationals. Number one, I've got 2 roots, but notice that if I have the plus root in the field extension, then I also have the minus root, right? Just by subtracting off and then adding back a. Agreed? So I don't have to worry about both roots, I just stick on one. And of course, since a over 2 is rational, I can forget that. And there we go, since 2 is rational. So this is actually q adjoined with the square root of a rational number. Now that I know that, I can go back to this. And so it all kind of reduces down. This doesn't work for qubits, right? It gets more complicated. And people study things, pure cubic extensions, and actually, even if it is a pure cubic extension, then you actually have to factor it into a square, and something square free is more complicated. But anyway, so if you have, continuing my example, for D is square free, so if you have Z side of Q, and then you have the quadratic extension, so with degree 2, then you have this guy. This is the integral closure in Z of Z in Q radical D, correct? What do we know? Because we're so smart now, we know that this is a Dedekind domain, right? Because it is the integral closure of Z and finite extension of a quotient field. Z is a Dedekind domain. So you might ask yourself this: self, what does this look like? And so, and this is kind of a fun exercise. It's natural to think, gosh, I wish this were Z adjoined with the square root of D, right? But sometimes that's not enough. So I'll tell you exactly what this looks like. This is kind of fascinating little ditty, but it also shows you quadratic. We've already seen the quadratics. Everything simplifies very nicely and comes together, but even quadratics are split into this weirdness. By the way, it's very easy to show that everything here is integral, right? Because radical D is integral, right? Because D is a square free integer. This is the root of the polynomial x squared minus D. If I can convince you that 1 plus radical D over 2 is integral in this case, then that should convince you that this extension is integral as well. Because once I know that animal is integral, the things in this look like n plus m times 1 plus radical D over 2. This is integral, so linear combination is integral. Right? So let me try to convince you of that. Suppose D is equivalent to 1 mod 4. I claim that this is integral. So if you look at I know what the root should be. Let's see if I put this together and get a monic polynomial. Cross your finger for me, will you? This is x squared. And then it's x times negative this, negative this. So let me write negative x and add them. That'll be easier. When I add these two things, I get, well, I get 1. And here's the real rub. What happens when I multiply these two things? I get 1 minus D over 4. So the polynomial I get, monic polynomial, or a monic polynomial I get. Now, at first, it may not look like this is a polynomial of the integers. However, this means that 1 minus D is equal to 4K. Because D is equivalent to 1 mod 4. Agree? So this polynomial is actually x squared minus x plus 4K over 4, which is x squared minus x plus k. So it's mine. Right? So what I have established for you so far is these two things are actually integral extensions of Z. Are they the integral closure? That one's a little bit trickier. So I challenge you, this sounds like something else, no homework. Think about this. Why is this it, right? I've shown that everything here is integral, but how come this is the entire subset of Q radical D that's integral, and for this case as well? So think about why that's true. Okay, any questions? All right. Oh, let me plug the math club. It's actually going to be about the in-body problem, which is very sexy. Say it that way. But the in-body problem is like a very important problem in physics that's actually known to be non-periodic in most cases, and there are some solutions. It should be a really good talk. It's an undergraduate research thing, so I encourage you to be there, and I'll see you on Friday. Okay.